Okay, so let's make a start then. So today episode 17, and we're looking at water storage tanks. So water supply options I covered in Sprinkler Talk number 3. So having a water storage tank is not the only option for having a water supply for your sprinkler system. However, it is by far the most common way of providing a water for your sprinkler system. But say if you want to have a look at some other options, then that's covered in Sprinkler Talk number 3. So you can go onto our YouTube channel or onto our website, I believe, and you can go look back through the previous episodes, and you can find that one. So we'll talk about things like using a town main supply, using a reservoir, using things like pressure tanks and what was the other one? Gravity tank, that's right, yeah. So there are some different options, but say water storage tank is by far the most common, and in many ways it's the best because we have all the water that we need. It's stored, so it's there, it's available. We can kind of see it and kind of measure it and have sensors on it, so we know it's there, and we have our automatic fire pumps to then deliver that water into the sprinkler system at the required pressure. So it's all very reliable and it's all very available, which is why water storage tank or tanks are the preferred option. The picture I've got on the screen here, again, it is one that I've shown you before, listing some of the common components of a sprinkler system. This one is showing a fairly typical property protection setup. So we can imagine this is some kind of a warehouse. So you can see there aren't any sprinklered zones, which is common. We've got it's fairly small. We've just got the one insulation control valve. So there's a maximum area that each initiation control valve can protect. And again, I've gone through those on a previous presentation. I can't remember off the top of my head which one that is, but a previous presentation I did look at all those kind of restrictions and limitations on sizes of installations and sizes of zones. So this is just a one completely open area, and then we have one water storage tank and one fire pump. Now, it does depend on what code standards you are looking at as to whether this would be appropriate or not, and it does depend again on what the application is. So for example, I know that FM protected jobs, so if you're using the FM standards, Factory Mutual, they're a big insurance group, and they would insure a lot of sort of specialised risks. They would call for 2 water storage tanks, but they would actually be looking for a duplicate supply. So they would want 200% of the water which has been calculated to be required for the system. So they need twice as much water, and normally that'll be stored in 2 completely separate water storage tanks, and they would have 2 pumps to be able to draw from both of those water storage tanks. And often it would be one electric pump and one diesel pump, so the diesel pump being the backup pump, or you could have 2 diesels. So that wouldn't be uncommon. So as I say, this one on the screen here is a way of doing it with one water storage tank and one fire pump. Again, on a previous presentation, we talked about life safety and the fact that life safety generally uses a superior twin water supply, where you've got 100% of the water required, but it's split into 2 half capacity tanks, and then you've got 2 fire pumps drawing off both of those sides. But say what we're concentrating on today is the water storage tank itself. So here's a few general points. So obviously it needs to be sized correctly for the sprinkler system. It can be oversized, if that's, generally speaking, you'd want to keep that tank as small as you can. But if you do have plenty of space, then there's no problem with it being slightly oversized. So, if that's a benefit, if you can kind of get an off-the-shelf tank which is a little bit bigger than you need, then that there's no harm in that. But we have to achieve the minimum effective capacity for the sprinkler system design. I'll talk about what effective capacity exactly means later on in the presentation. But yeah, all of this is calculated either by using this kind of table method that we have in 12845, which will kind of give a general calculation. And because it's a general calculation, you say, well, okay, I've got a building of this size, of this height, of this hazard category, therefore I'm going to need this amount of water. So because it's like quite a quick general kind of way of doing it, there is what I call a fudge factor built in, which means you're always going to end up with a slightly larger tank than you necessarily need, because you want to make sure that it's covered. Or you can use FHC, full hydraulically calculated methods, where you can actually look at the specific design that you've done and work out, okay, well, the maximum area of operation is this. This is my worst case as far as the tank is concerned. So this is where I'm going to be discharging the most water from. And of course, we need to meet the duration factor of the sprinkler system. Ordinary hazard is 60 minutes. So, we'll be saying, okay, well, these sprinkler heads here in this area are going to operate for 60 minutes, and therefore I need this size of tank, say effective capacity. Generally, it's filled from an external source using appropriate ball or float valve. Float valves is what I call them. Some people call them ball valves. For me, that kind of gets a bit confusing because we do use ball valves on sort of the smaller bore pipe. So often the drain valve connections on a sprinkler system will be a ball valve. A proper ball valve, say in my world, which is actually where you have this silver the ball inside, and when you turn the handle, it's that ball with the hole through that's actually opening and closing. For me, that's a ball valve, and the valves that are used on tanks for me are float valves. But say some people call them ball valves, and I guess both terms are kind of interchangeable. But yeah, I call them float valves because they work just like the cistern on your toilet at home, where we have a float, and depending on the water level, that float will rise and fall, and that will actually open and close the valve. So it's automatic filling system. So as the water level drops, the valve opens, it refills, and then the water level rises, and that valve will shut the valve off. Not foolproof, of course. We do need to think about what happens if the arm breaks and the valve fails. So that we do need some overflows in there and kind of thoughts in terms of what do we need to do to make sure that we're covered. But yeah, obviously that is the general way that they are set up, and of course they're generally very reliable. And part of the reason why we use that kind of float valve arrangement is to do with water regulations. We don't want, as soon as that water goes into the water storage tank, it's dirty water. It's classified as dirty water. If you want to look more into that, there's different water categories for different sorts of dirty water. But yeah, if it's in the town main, it is clean, category 1, drinking water quality. As soon as it enters that water storage tank, it becomes category 2, 3, 4. So it becomes dirty. So we don't want that water to then come back into the town main. So we can use a non-return valve, but the easiest thing to do is just to use gravity, basically, and that's what the float valves are doing. The water is falling from the float valve into the tank. The water can't jump back up again into the valve. And as I said, there'll be an overflow to stop the water level reaching that level. Metal tanks protected against corrosion. Pretty self-explanatory. And then I won't go through all of these things, but these are some of the points that I've picked up from the rules in terms of what is required. Tank level indicator, that can be electronic, or it could be an actual pipe that goes outside, or often it's both. We've got the digital readout and we've got the actual sort of physical level that we can normally put like a coloured ping pong ball into the pipe, which is a clear pipe, so you can then see clearly the level of the water within there. Facility to drain down, access to the incoming valves, controls applied. So for the float valves need to be tested as part of the regular maintenance. So that's why we have the ladders up the side of the tank often, so you can actually get up there to inspect the float valves. Normally what you do is you manually operate them to just check that they are working correctly. Yeah, clearly marked and labelled. I'm not quite sure I put 65 there. I think that's probably just lent on my keyboard or something. But yeah, clearly marked and labelled, so that the tank has got to have the manufacturer's name, the date of manufacture, the material it's made from, details on any kind of linings that's in there, what its effective capacity is. All those kind of things should be clearly marked on the outside of the water storage tank. A few more points. Go on PowerPoint, let's go. Tanks need to have a roof on them. The roof's got to be rigid. It's got to exclude direct daylight. Again, that's because of bacteria in the water. If you can keep the daylight out, then the bacteria can't thrive. Prevent water from being contaminated with extraneous matter. We don't want plants, mud, stones, bicycles, whatever. We don't want anything like that in the tank. It can block the tank up, so it can stop the water from actually getting to the pump, and also little bits are going to get sucked through that line into the pump, and that's going to damage the pump, or in extreme cases it's going to break the pump. And of course that pump is there to provide protection, fire protection. So if the pump breaks because there's stones in the tank, then we've lost our sprinkler protection. So that's obviously not a good thing. Lockable access hatch, for inspections and for cleaning, and designed to withstand wind, rain, and snow. There's actually there's like a little section about snow. You've got to allow for a certain amount of snowfall and the weight sort of resting on the outside. But obviously, if your tank is inside, then I'm guessing you don't have to worry about that particular aspect. Tank liners. So tank liners, again, you don't have to use a tank liner in a water storage tank for sprinklers, but they are very commonly used because otherwise you would have to kind of coat all of the surface of the inside of the tank. So an easy way of doing it is just to use a tank liner, which is basically like a big plastic bag. So it's a synthetic EPDM reinforced PVC or butyl rubber liner. So it's a hard wearing plastic rubber kind of material, and it's factory fitted if you're buying a tank off the shelf. If that line needs replacing, then they'll drain all the water off and they'll basically pull that liner off and put a new one in, or more commonly they'll just put a new liner over the top of the old one if it's got a hole in it. But essentially it's just a big plastic bag, and it's to stop the water from touching the pipe, touching the sides of the tank, and obviously that's going to stop. Well, it's going to help stop corrosion of that tank. We don't have to worry so much about coating the tank and preventing the water touching it. So options then. So we can use a cylindrical steel water storage tank. So these are quite a common sight if you're driving around in the car and you're sort of looking out over industrial kind of areas. You will see this kind of cylindrical steel tank. Now, of course, it doesn't have to be sprinkler related. It could be storing fuel. It could be storing water for irrigation. could be storing any number of things, but yeah, these are commonly used, but also for sprinkler systems for storing water. So they're available in a range of materials, but say generally we're going to go down the kind of cheaper option, coated steel or galvanized steel, and then just use a liner on the inside. They're bolted. The sections are bolted together, or kind of riveted together. It eliminates the need for welding. That's the point. In the past, these kind of tanks would be welded together. So obviously you would need a skill there. You'd need to hire a welder to come onto site, and obviously that would take a lot of time to put together, and obviously the cost would increase. So the fact that now they're in sections and it can just be bolted together just speeds up the process. This is something I learnt when I was preparing for this, is that they're basically assembled from the ground up. So you kind of do the top ring first, and that will sit on the floor, and then you sort of jack it up in the air, and then you put the next ring in, and then jack it up, and you just keep going like that. So you're basically building from the ground up, and again, that's good from a kind of health and safety point of view. People aren't having to work so much at height, and also that's going to speed up the process, because you can easily kind of walk around the outside. You don't have to get all that kind of lifting gear in place to start bolting it together 20 meters up in the air. It's shipped on pallets in various sections, and again you can get off-the-shelf designs, or you can work with a company to actually make a sort of bespoke one that's exactly the right size. Obviously, you've got a choice between sort of a small diameter and a large height, or a low height and a large diameter. It again depends on the space you've got available. But obviously, the taller they are, the more sort of structural bits you need to kind of worry about for the supports. Need to have a decent base as well to fit these on. Of course, there's a lot of weight going down to the ground, so that needs to be thought of as well. Sectional GRP, glass reinforced plastic, water storage tanks. So again, these are quite common, particularly when you've got the tank inside. So in a kind of basement level, you would have these sort of sectional GRP tanks. These are constructed using hot press compression molded glass reinforced plastic. So basically they're injection molded. It's that kind of squeeze a bit of plastic out and then squash it into shape. Generally, they are externally flanged tanks. So that one in the background there is externally flanged. So all the bolts are on the outside. But you can also have totally internally flanged, TIF. That means that the flange is on the inside. That means that when you're assembling the tank, you have to kind of climb in on the inside to fit the bolts. But what it does mean is that you can fit it in a tighter space. So you can push it up against a wall, and you can get inside the tank to tighten up the bolts. If it's externally flanged, then obviously you need 500 millimeters around the outside, so that when it's assembled, you can actually get somebody in around the sides to tighten up the bolts and to assemble it. So yeah, you've got some options there. Often, you see that this one in the background here is externally flanged, apart from the bottom. So I think there will be an internal flange in the bottom of that tank, so that it can sit flat on the floor. Otherwise, you're going to have sort of flanges poking out into the bottom, so it wouldn't sort of sit flat on a concrete base. The sections are bolted together, and obviously there's some sort of sealant in the inside. That's often like a tape, and again this kind of butyl tape that you'll peel off and stick down before you tighten up the bolts. You can also use sort of rubber gaskets to again custom cut to fit, but I think it's more common to use this kind of tape to do it. And again, these are sort of stock items. So often there'll be a sort of standard sizes of panel. and you can assemble these together to create a whole variety of different shapes and different sizes of tank. So again, they're quite cheap because they are kind of mass produced. Concrete water storage tank. So again, you can use a concrete tank. Again, not very common for sprinkler systems, and I think that's down to the amount of faff. Really, it's going to be more expensive to make, and you can use a liner, but also you need to protect that concrete from corrosion because they are quite chemically sensitive. The one good thing about a concrete tank is you can install it below ground, which is the picture just showing you here. But yeah, I mean that does save you some space, but as I said there, it's not ideal for positive head conditions, and obviously maintenance then becomes tricky because if there's any issues, you've got to sort of dig up the tank to kind of get into it. This slide here is just showing you some of the components. So we've got the ball valves at the top, which I call float valves. We've got the access ladder to get up the side, an access panel for getting in an inspection when required. Say foundation, purposely made and calculated for weight. The contents gauge is looking like a high and low tank level, for example. An immersion heater may well be used. You will need to keep that water from freezing. So the easiest way of doing it is just having a small immersion heater in the side, and that's obviously got a temperature sensor. So when the temperature outside, say, drops to 5 degrees, that will kick in. An overflow and telltale. So yeah, we do need an overflow in the tank, and this one is, it needs to be discharged in a way that's safe, but also that it's very obvious so people can see it and go, oh, that tank's overflowing, and do something about it. But also that the high and low tank levels will sort of see to that as well. We need a drain valve connection, obviously at the bottom of the tank. And yeah, that incoming water supply, so this one hasn't been sort of fully finished yet, so that will be connected into the ball valves at the top when they're ready to do so. Effective capacity then. So this term is basically meaning the useful amount of water. So just because we've got a tank with a volume of say 10,000 litres, that doesn't mean that we've got all that water available to us. We can't count the very top of the tank because often that's where the overflow arrangement is. We have an air gap as well to the float valve, so we can't fill it. We can't use the water all the way to the top of the tank because there's always going to be a gap there. And we can't use the water all the way to the bottom either, because in this instance here, we've got a pipe coming in from the side. So obviously when that water drops below the top of that pipe level, then it's not going to be quite the same as it was before. And the pump needs that kind of constant force of water coming through to basically prime it. Otherwise, it's kind of dragging in air. These fire pumps don't like pumping air, so the pump will what's called cavitate. It basically means it'll implode or it'll break apart. So we have what's called an effective capacity. There's lots of details of that in the British Standard, which will say if your pipe is here, then you need to go. I think it's to do with the diameter of the pipe. You go 2 times the diameter of the pipe above from that point. And that's where you say your effective capacity starts. And at the top, again, you count down, 300 millimeters from the highest level. And that is then your effective capacity. So that's what you need to specify. When you're asking a tank manufacturer to make you a tank, the volume is not as important as the effective capacity. Things you can do to improve the effective capacity is one, to use a Vortex Inhibitor. So you're going to kind of turning the pipe down so it's kind of pointing down. And that's what a Vortex Inhibitor looks like. What does it do? It inhibits vortexes. So it basically stops the water from spinning. I don't know massive amounts about this, but when the water starts spinning, it kind of the water levels change, and the water level kind of bends down at the top. I think essentially the water level becomes unstable. And when the water level becomes unstable, there's obviously a risk that will start dragging air through the pipe. So the vortex inhibitor stops the water from spinning, as it would do down a plug hole. When you've just had a bath, you pull the plug out, the water spins round. So this is going to stop that from happening, which means again we can use more of the water. We could also use some kind of sump arrangement like that. So again, we're just increasing the effective capacity by just having a small area where we're actually sucking the water out from that's lower than the rest of it. Reduced capacity tanks. So if this is an option. Again, you can't always use a reduced capacity tank. So for example, for life safety, you wouldn't be able to use reduced capacity. But other property protection avenues you would. The idea is that you are looking at the infill of the tank and you are calculating that during the duration of the activation, and you are saying, okay, well, my water tank needs to last for 60 minutes, but obviously we're taking water from the bottom, and whilst those 60 minutes are ticking round on the clock, the infill is actually topping my supply back up again. So I can count that infill as part of the water storage. So this example here, we're saying it's an OH3 installation, the highest sprinkler at 20 metres, which means that the table 9 figures show that we need 160 cubic metres of water. And then the duration is 60 minutes. We have an infill of 600 litres per minute. There's a minimum capacity listed, so that we can't go any smaller than 30 metres cubed, but as you'll see from my calculations, that seems pretty unlikely to me. So in 60 minutes, the infill would provide 36,000 litres, which is 36 metres cubed, and therefore we can reduce the tank capacity to 124 cubic metres. So, we've made a small difference in the size of the tank required there. Obviously, the bigger your infill, the faster you can get water in, the more effect that you will have. But it seems to me that you're going to need a whopping infill to get anywhere close to kind of the minimum capacity that's listed. So in this instance here, I imagine you would shrug your shoulders and say, well, it's not made a massive difference, therefore we may as well just have a full capacity tank and not worry about the infill. But that's how you do it anyway. Positive suction is something that I've mentioned before, and I said that underground tanks are going to be difficult to achieve positive suction head. So where possible, this is the conditions that we're looking for. If it's not feasible, if we can't do it, then we can have to use suction lift conditions or use submersible pumps. But this is where we want to be typically, where we have at least 2/3 of the effective capacity of the tank above the pump centre line, and the pump centre line no more than 2 metres above the low water level on the suction tank. So the diagram on the left is obviously just a diagram, but you can clearly see we've got most of the water above the centre line of the pump. So what that means is basically it's self-priming. Okay, that water is pushing down onto that pipe. So as soon as that pump starts, it's going to start sucking water out, and that water again is kind of it wants to go down that pipe, if you like. Just from a physics point of view of the gravity pulling down on the water, it's going to want to go that way. So that's how you want to operate, so that the pump has always got water to it. This is showing you suction lift conditions. So again, we're having to lift the water out of the tank and then into the pump. So that there's a few notes there on the left-hand side. But basically, all you need to know is that this is not preferred because there's again just more to go wrong. I think that's the thing about sprinkler systems. We don't like it when we introduce things that could go wrong. So here we have to have a separate priming tank for our pump, so that when the pump starts, it's got water available to it under positive head. So we've got a smaller tank above the pump, which is providing it that positive head to kind of get it going. Once it's going, it can then obviously lift the water out of the tank below. But something else to go wrong. And that is it for today. Again, hope you find that useful. Little tour of water storage tanks. Next week, we're going to be looking at sprinkler heads part 3. So this is basically covering anything that I haven't already said about sprinkler heads. So yeah, I did make a list of that in a previous presentation. So I'll be referring back to that list to make sure I cover those points. But yeah, I hope you can join me next week, and we'll be talking about sprinkler heads part 3. I can see a couple of comments coming in, so I'll have a quick read of those. Yeah, good. So thank you. I got a comment here reminding me that about the categories of water. So we need a non-return valve on the supply line to the sprinkler tank, which is quite right. So we have the float valves, which are providing essentially a non-return valve into the tank, but we also need a non-return valve on that supply line as well. So that would be required. We are aware of that through our BellCheck product. Our BellCheck product automatically tests the alarm valve, and when it's on a town main supply, we are relying on that non-return valve on the incoming supply to actually push against to actually make our product work. So on occasion, the BellCheck has not worked, and we've said, okay, well, have you checked your non-return valve on the town main supply? And when they've checked it, actually found that it's not working anymore. So yeah, in a way, we kind of done them a favour really by pointing out that that this component has failed, and then once that's replaced, then our product will work. But I can't say just pushing against it to keep it closed while we're doing our test. Okay, it looks like that's it. So yeah, thanks again for tuning in. Thanks for listening. And yeah, I'll see you next week for Sprinkler Heads Part 3. All right, bye-bye.